Imagine a universe in motion, galaxies spinning, colliding, and drifting through the cosmos over billions of years. From the first sparks after the Big Bang to the majestic spirals of the Milky Way, every star, every halo, every cosmic dance tells a story. Join us as we journey across time and space, witnessing the universe in its full glory. This isn't just astronomy, it's the story of existence itself. Are you ready to see the galaxies come alive? Hello there, and welcome back to Dreamy Science Stories, a quiet harbor for curious minds, a soft place where questions drift like constellations and answers arrive gently, like starlight crossing an ancient sea. If this feels right to you, then you are already exactly where you need to be. Let your shoulders loosen. Let your breathing grow slow and unhurried. Feel the steady rhythm of your body here on Earth, while your thoughts prepare to travel far beyond it. Tonight, we are not just looking at the stars. We are leaving the familiar spiral of our own galaxy and wandering into the wider archipelago of the universe, into realms so vast that even imagination hesitates at their edges. We will drift among silent dwarf galaxies, faint and fragile as cosmic whispers. We will circle colossal spirals, turning with patient grace through the dark. We will pass shattered remnants of ancient collisions, still glowing softly from impacts that happened before our planet had oceans. We will explore invisible halos of dark matter, structures made not of light, but of gravity itself. We will stand before black holes that flicker like distant cosmic candles, and we will peer toward newborn galaxies forming at the very rim of the observable universe, their light only just arriving after a journey longer than Earth has existed. Some of what you hear tonight may feel strange, almost dreamlike. Some details may shimmer with quiet wonder. Others may settle softly in your mind, like an old memory resurfacing in the dark. But every story is real. Every phenomenon we describe is written into the structure of space and time. Each one is a quiet echo from a universe still unfolding. And if this journey helps you rest, if it slows your thoughts and steadies your breath, consider liking and subscribing. It allows other wandering minds to find this place of calm exploration too. Now, if you are ready, let your awareness expand outward. Let your breath fall gently, like starlight settling across a distant world. And together we begin. Far across the cosmos, there exist galaxies whose central black holes shine brighter than all the stars around them combined. These extraordinary objects are known as quasars. At the heart of many galaxies lies a supermassive black hole, a gravitational abyss so dense that even light cannot escape once it crosses the threshold. Most of the time, these black holes are quiet, almost invisible, but sometimes they awaken. When vast clouds of gas and dust drift too close, gravity pulls them inward. The material does not fall straight in. Instead, it spirals, faster and faster, forming a glowing disk around the black hole. Friction and compression heat this swirling matter to millions of degrees. It blazes with radiation across the electromagnetic spectrum, radio waves, visible light, X-rays. And when the feeding becomes intense enough, the galaxy transforms into a quasar. It is not the black hole itself that shines. The black hole remains dark, as it always does. The light comes from the infalling material, heated to extraordinary temperatures as it races toward oblivion. Around this central furnace, twin jets of high-energy particles can erupt, shooting out for thousands of light years into intergalactic space. For a time, sometimes millions of years, the galaxy's core becomes one of the brightest objects in the universe, a beacon visible from billions of light years away, a lighthouse shining across cosmic time. Some quasars radiate more energy than 1 trillion suns, and yet, all of that brilliance is powered by darkness. There is something quietly humbling in that thought, that immense light can be born from gravity's deepest well, that destruction can produce illumination, that in the universe, opposites are often intertwined. Closer to home, something quieter, but no less profound, is happening. The Milky Way is currently in the middle of a slow-motion feast. A small companion galaxy, known as the Sagittarius dwarf spheroidal galaxy, has been orbiting ours for billions of years. It is faint, delicate, easily overlooked. But gravity does not overlook. Each time the Sagittarius dwarf passes through the Milky Way's disk, our galaxy's immense gravitational pull tears away more of its stars. Long, shimmering streams of those stars now wrap around the Milky Way like pale ribbons, vast stellar currents tracing the path of a galaxy being gradually dismantled. The Sagittarius dwarf has already passed through us several times. Each crossing strips it thinner. Each orbit leaves it weaker. It is not a violent destruction, not an explosion or sudden collapse. It is a slow unraveling, stretched across millions of years. A quiet assimilation. Its stars do not vanish. They become part of us. By studying these stellar streams, astronomers reconstruct the history of our galaxy's growth. The Milky Way did not form all at once. It grew by merging, by absorbing, by drawing smaller galaxies into itself over billions of years. The night sky you see above you is the result of countless events like this: collisions, mergers, accretions, each one adding to the grand structure we now call home. Even now, the Milky Way continues to change. Even now, it is reshaped by what it draws in. And so are we in smaller ways, formed by what we absorb, shaped by what becomes part of us over time. Sometimes, when galaxies merge, their central black holes meet, but they do not immediately combine. Instead, they begin a slow dance. Two supermassive black holes orbiting each other deep within the newly formed galaxy. A binary system hidden at its core. For millions of years, sometimes far longer, they circle in tightening spirals, pulled together by gravity, yet still distinct. Astronomers have detected several such pairs. In some cases, both black holes are active, glowing as twin points of intense radiation. In others, their presence is inferred from the subtle motion of nearby stars, or from slight shifts in emitted light. Eventually, gravitational radiation, the faint rippling of space-time predicted by Einstein, carries away energy from the system. The orbit shrinks, the spiral tightens, and at last, the two black holes merge in a cataclysmic release of gravitational waves that ripple outward across the fabric of the cosmos. Until that moment, they orbit quietly, twin hearts beating inside a single galactic chest. Rare, powerful, patient. In the vast darkness between galaxies, there are stranger structures still, galaxies that contain almost no stars at all. They do not shine. They emit no visible glow. There are no sparkling clusters, no luminous arms. And yet, they are there. These are dark matter galaxies, objects composed almost entirely of the mysterious substance that outweighs ordinary matter throughout the universe. Dark matter does not emit light. It does not absorb it. It does not reflect it. It reveals itself only through gravity. Astronomers discovered these invisible galaxies not by seeing them, but by watching how they bend the light of more distant objects behind them, a phenomenon known as gravitational lensing. They distort the fabric of space-time, subtly warping background galaxies like images seen through rippling water. Some dark galaxies reveal themselves by tugging gently on neighboring systems. Others are inferred from patterns of motion in nearby gas clouds. We do not yet know exactly how they formed. They may be failed galaxies, structures that never ignited stars, or remnants of others long stripped of visible matter. They drift through space like silent islands of gravity, mass without light, presence without visibility, a reminder that most of the universe is unseen. And even our own galaxy is not immune to the larger tides of cosmic motion. The Milky Way is being stretched, ever so slightly, by the gravity of nearby galaxies, most notably by Andromeda, our massive neighbor drifting slowly toward us across the void. These gravitational interactions are known as tidal forces. similar in principle to the moon's pull on Earth's oceans, but magnified to galactic scales. Over millions of years, these tides have warped the Milky Way's outer disk, creating subtle waves and ripples in its spiral arms. Some stars are nudged from their paths. Gas clouds shift and drift. It is not violent. It is patient, a slow reshaping of structure over unimaginable time. Even galaxies feel the pull of others. Even systems hundreds of thousands of light years wide are connected. Nothing exists alone in the universe. Everything moves. Everything influences everything else. And yet, for all its vastness, the Milky Way is not among the largest galaxies known. Some galaxies dwarf ours beyond easy comprehension. IC 1101, for example, stretches more than 6 million light-years across, over 100 times the diameter of the Milky Way. It sits at the center of a massive galaxy cluster. Surrounded by countless smaller companions, it has gradually absorbed over billions of years. These giant ellipticals did not grow large by forming stars alone. They grew by merging, again and again, consuming dozens, perhaps hundreds of smaller galaxies. Their cores are dense and ancient, filled with aging red stars. Their outer regions extend into faint halos where lonely stars orbit in enormous, slow arcs. To imagine such a structure is to feel very small. And yet, within that smallness, there is peace. In a universe where galaxies themselves can be middle-sized, our existence becomes both fragile and extraordinary. Some galaxies live fast and bright. While the Milky Way forms perhaps 1 or 2 new stars each year, certain galaxies enter explosive periods known as starbursts. During these episodes, hundreds, even thousands, of stars ignite annually. Dense clouds of gas collapse under gravity in rapid succession. Ultraviolet light floods the galaxy. Dust glows hot and bright. The core becomes a furnace of creation. These bursts are often triggered by collisions, when 2 galaxies pass through one another and stir up their gas reservoirs. But such brilliance cannot last. Starburst galaxies burn through their fuel quickly. Once the gas is consumed or expelled, the frenzy ends. The galaxy settles into a quieter phase. For a brief moment in cosmic history, they blaze like fireworks. Then they fade. Even galaxies have seasons. At the center of our neighboring galaxy Andromeda lies a supermassive black hole larger than our own. The Milky Way's central black hole, Sagittarius A*, has a mass about 4 million times that of the Sun. Andromeda's central black hole is at least twice as massive, possibly far more. Both are currently quiet. They are not actively feeding. They do not shine like quasars. But in the distant future, about 4 billion years from now, the Milky Way and Andromeda will merge. Their stars will interweave. Their gas clouds will collide. And deep within the new combined galaxy, their 2 central black holes may spiral together, eventually merging into one even greater gravitational giant. 2 galaxies, 2 dark hearts, one shared future. A reminder that even on cosmic scales, change is inevitable. And when we look deep into space, farther than any nearby galaxy, we are also looking backward in time. Light does not travel instantly. It moves at a finite speed, about 300,000 kilometers per second. Fast beyond comprehension, yet still limited. The light from the most distant galaxies visible to our telescopes has been traveling for over 13 billion years. When we observe them, we do not see them as they are now. We see them as they were when the universe itself was young. Looking into deep space is like opening a time capsule. Each distant galaxy is a message sent long ago. Each photon that reaches us is a traveler that began its journey before Earth had formed, before the Sun existed, before even our galaxy was fully shaped. And here you are, on a small world orbiting an ordinary star in a middle-sized galaxy, able to receive those ancient signals. The universe has been unfolding for billions of years. And tonight, in quiet reflection, you are part of its ongoing story. Far beyond the soft glow of our own night sky, beyond the quiet shimmer of the Milky Way, there exist galaxies so distant that they appear in our most powerful telescopes as nothing more than faint smudges. Tiny strokes of red light brush delicately onto the canvas of deep space. They are dim, stretched by cosmic expansion, their light pulled toward the crimson end of the spectrum by the slow breathing of the universe itself. When we look at them, we are not seeing what they are. We are seeing what they were when the cosmos was still young, only a few 100 million years after the beginning. In those early epochs, galaxies were not the grand spirals and glowing ellipticals we know today. They were smaller, restless, chaotic gatherings of gas and dust. They flickered with newborn stars that blazed hot and brief, illuminating a universe just emerging from darkness. There was a time known as the Cosmic Dark Ages, when the first light had faded and stars had not yet fully risen. The universe was filled with neutral hydrogen, quiet and opaque. Then slowly these early galaxies began to glow. The first generations of stars ignited within them, massive, brilliant, short-lived beacons that poured ultraviolet light into space. Their radiance transformed the cosmos, ionizing the surrounding gas, lifting the great veil of darkness. These galaxies ended the Dark Ages. They were the dawn. And somehow, across more than 13 billion years of expansion and cooling and cosmic change, their ancient light has reached us. It has traveled across incomprehensible distances, slipping through widening space, surviving collisions and absorption and time itself. To catch even a whisper of that light is to hold a message from a universe still learning how to become what it is now. Our own galaxy carries the memory of such ancient times within its structure. The Milky Way did not form in a single, graceful moment. It grew, slowly, patiently. Through gravity's persistent pull, it merged with smaller galaxies, drawing them in, unraveling them, absorbing them into its growing halo. If we could see with different eyes, we would notice delicate, elongated streams of stars wrapping around our galaxy like ghostly ribbons. These stellar streams are the remnants of long-lost galaxies, stretched thin by tidal forces, their once coherent forms dissolved into arcs of light. They loop and spiral through the galactic halo, faint and nearly invisible, yet traceable through careful measurement. One such companion, the Sagittarius dwarf spheroidal galaxy, is still in the process of being consumed. Its stars are gradually woven into the Milky Way structure, leaving behind a stellar trail that whispers of its former independence. Other streams are older, more diffuse, ancient scars from collisions billions of years past. By mapping these streams, astronomers reconstruct the Milky Way's biography. Each ribbon of stars is like a fingerprint pressed into cosmic dust. Each arc is a memory of gravity's quiet conquest. We drift within a galaxy shaped by devouring and becoming, a galaxy still growing. And the story is far from finished. Out beyond our galactic neighborhood, another vast spiral drifts steadily toward us, the majestic Andromeda Galaxy. Even now, it approaches at nearly 100 kilometers per second, drawn toward us by mutual gravity. It is not a sudden catastrophe waiting in the wings. It is a slow dance already underway. In about 4 billion years, the Milky Way and Andromeda will begin their long embrace. They will pass through one another not in explosive destruction, but in a sweeping gravitational ballet. Stars, separated by enormous distances, will mostly avoid direct collision. Yet their orbits will shift. Spiral arms will stretch and twist. Vast clouds of gas will collide, compress, and ignite in bursts of star formation. For hundreds of millions of years, the two galaxies will tangle, separate, and return again. Eventually, they will settle into a new form, a single, larger elliptical galaxy, sometimes nicknamed Milkomeda by astronomers. A new home born from two ancient spirals. Our solar system may survive, carried gently into a different region of this merged galaxy, watching new constellations form in a reshaped sky. The drama unfolds at the pace of galaxies, measured not in lifetimes but in epochs, and it has already begun. Yet not all galaxies blaze with starlight. Some drift quietly through space composed almost entirely of cold hydrogen gas. These are the so-called dark galaxies, objects with mass and motion, yet with few or no stars to illuminate them. They are detected not by visible light, but by the faint radio emissions of hydrogen atoms, whispering at a wavelength of 21 centimeters. These ghostly systems are puzzling. Perhaps they are galaxies that never managed to ignite sustained star formation. Perhaps they are remnants, leftover reservoirs of gas from past mergers. Or perhaps some internal process prevented stars from forming at all. Whatever their origin, they represent a strange and quiet possibility, structure without brilliance, form without fire. They float between luminous galaxies like dark clouds awaiting a spark, suspended in a state of almost being. Invisible potential drifting. Sometimes galaxies reveal themselves not by light, but by gravity alone. When a massive galaxy lies between us and a more distant source, its gravitational field bends the background light, curving space itself. This phenomenon, gravitational lensing, creates arcs, rings, and mirrored images in the sky. Through this bending of light, we detect galaxies too faint or dust-shrouded to see directly. They become visible by the distortion they impose upon the universe behind them. In some cases, the lensing galaxy is rich in dark matter, its invisible mass shaping the curvature of space more strongly than its visible stars ever could. These natural cosmic lenses magnify the distant universe, allowing us to study galaxies that would otherwise remain beyond reach. In observing the bending, we learn about both the foreground galaxy and the far-off light source. It is gravity acting as a storyteller, revealing hidden characters through subtle distortions. At the centers of many galaxies, including our own, lie supermassive black holes. When gas and dust spiral toward these dense cores, they form glowing accretion disks, heated to extraordinary temperatures. And sometimes, from the magnetic chaos surrounding this infalling matter, twin jets of particles erupt outward. These jets do not emerge from within the black hole itself, but from the intense environment just outside it. Magnetic fields twist and concentrate energy, launching beams at nearly the speed of light. They can stretch for millions of light years, far longer than the galaxy that produced them. In radio images, they appear as luminous threads piercing intergalactic space. They heat surrounding gas, shape galaxy clusters, and regulate star formation across enormous distances. Some of the largest structures known in the universe arise from these jets. And yet, they begin in a region smaller than our solar system, a tiny, brilliant nexus where matter meets gravity and ignites extraordinary forces. When we peer as far back as possible, we find galaxies that formed astonishingly early. The oldest known so far emerged just a few 100 million years after the Big Bang. One such ancient system dates to roughly 320 million years after the beginning, a remarkably short time in cosmic terms. Its light has traveled for more than 13 billion years to reach us. It is small, rich in young stars, and surprisingly organized. Observing it allows astronomers to glimpse the era when galaxies were first assembling from cooling gas clouds. Each new telescope extends our vision deeper into time, revealing ever fainter structures at the edge of visibility. Some galaxies are born not from pristine gas, but from debris. When larger galaxies interact, tidal forces can pull stars into long, luminous tails. In certain cases, these stripped stars and gas clouds collapse together, forming new systems known as tidal dwarf galaxies. Unlike most galaxies, they do not begin as fresh collapses in the early universe. They are composed of recycled material, stars once belonging to other galaxies. They may contain little dark matter and may not endure for billions of years. but for a time they shine, stitched together from borrowed histories. There are also galaxies that seem to spin against expectation. Most systems rotate in harmony with the gas from which they formed. But some exhibit counter-rotation, their central regions or disks turning opposite to the surrounding material. Such patterns often arise from mergers, when incoming matter carries its own angular momentum and resists alignment. These counter-rotating galaxies are rare. They are quiet anomalies, twists in the cosmic narrative preserved in stellar motion. And surrounding many galaxies are globular clusters, dense, spherical gatherings of ancient stars. Our Milky Way hosts around 150 of them. Giant elliptical galaxies may harbor thousands. Each cluster is a relic from the galaxy's early epochs or from systems it once absorbed. They orbit like silent satellites, compact and enduring. Within them are some of the oldest stars in existence, stellar fossils that formed when the universe was young and metals were scarce. When we look up at the night sky, we see a tranquil scattering of stars. But beyond our vision lies a universe in motion, galaxies merging, streams stretching, jets firing, light bending, gas drifting, clusters orbiting. It is a universe shaped by gravity and time, by quiet collisions and slow transformations. And we, on a small planet orbiting an ordinary star, are witnesses to it all, arriving late in cosmic history, yet capable of tracing its story back to the dawn. We are not separate from this vast unfolding. The atoms in our bodies were forged in ancient stars, perhaps in galaxies long since consumed. In that sense, we are children of mergers and collisions, of early light and dark ages ended. And as we drift gently through the Milky Way, itself drifting through space, we continue to move within echoes billions of years old. Travelers inside a story still being written across the silent, expanding dark. In the farthest reaches of a galaxy's halo, where starlight thins into darkness and distances are measured in tens of thousands of light years, there drift small, ancient companions, globular clusters. They may appear modest beside the grandeur of spirals and ellipticals, yet in a quiet and profound way, they are memory keepers. Each globular cluster is a densely packed sphere of stars, bound tightly by gravity, moving together through space like a slow, celestial heartbeat. Within them are some of the oldest stars in existence, embers from an era when the universe was still young and metals were scarce. Their chemistry is simple, primordial. Their motions are stable and patient. Some of these clusters may even predate the fully assembled galaxy they now orbit, forming in the earliest stages of galactic construction, when matter was still gathering and gravity was sculpting the first structures from the cooling cosmos. When astronomers count these clusters and measure their ages, compositions, and orbits, they begin to reconstruct the biography of a galaxy. Each cluster becomes a fossil record, evidence of mergers long past, of swallowed companions, of early bursts of star formation. Tiny though they are against the vastness of a galactic halo, they carry stories billions of years old. They circle silently in the outer darkness, like lanterns preserving the deep past. But not all galactic centers are so quiet. At the heart of certain galaxies, supermassive black holes awaken. Instead of resting in shadow, they begin to feed, drawing in gas and dust that spiral inward, forming a luminous accretion disk. As this material falls closer, it heats to extraordinary temperatures, glowing fiercely. The result is an active galactic nucleus, an AGN, capable of shining brighter than all the stars in its host galaxy combined. Yet these brilliant cores are not steady flames. Some flicker. They flare and dim over years, days, even hours. The changes arise from the unpredictable flow of matter into the black hole. Sometimes gas surges inward in abundance. Sometimes the supply falters. In rare and remarkable cases, astronomers have watched galaxies transition from active brilliance to quiet dormancy, and then back again. It is like observing a distant lighthouse across a dark cosmic ocean. A pulse of light, A pause. Another flare. The black hole itself remains invisible, but the dance of matter around it becomes one of the brightest beacons in the universe, at least for a while. Even the darkest objects can blaze when conditions align. Closer to home, our own Milky Way presents an image of graceful permanence. Its spiral arms sweep outward in elegant curves, cradling stars, gas, and dust in luminous arcs. From our vantage point within one of those arms, they seem like enduring structures, cosmic architecture carved into space. But the arms may not be fixed structures at all. According to density wave theory, they are patterns, regions of higher density that move through the galaxy like traffic waves on a highway. Stars orbit the galactic center at their own speeds, drifting in and out of these denser regions. As they enter an arm, they slow slightly, bunching together. As they exit, they spread apart again. The spiral shape persists, but the individual stars within it are constantly changing. In this sense, the arms are not solid sculptures. They are living patterns, currents in a vast stellar sea. Other models suggest that gravitational interactions, bursts of star formation, or even past galactic encounters can cause arms to form, dissolve, and reform over time. Whatever the precise mechanism, the Milky Way is not static. It is dynamic, breathing, shifting gently as billions of stars trace their slow orbits, and we are carried along within that motion. Surrounding our galaxy are smaller companions, dwarf galaxies bound by gravity, orbiting like moons around a planet. Some contain only a few million stars, others hold a few billion. Compared to the Milky Way's hundreds of billions, they are delicate systems, faint and easily overlooked. A few, like the Large Magellanic Cloud and the Small Magellanic Cloud, are visible to the naked eye from the southern hemisphere, appearing as pale patches against the night sky. Others were discovered only recently, their dim light revealed by careful surveys. Some dwarfs may be remnants of once larger galaxies, stripped of stars and gas through repeated interactions. Others could be primordial fragments, leftovers from the earliest stages of galaxy formation, surviving in relative isolation for billions of years. Over immense spans of time, many of these dwarfs will be drawn inward. They will lose stars to tidal forces, their structures stretched into streams, eventually merging into the Milky Way itself. But until that day, they trace long arcs through the galactic halo, ancient travelers moving within a larger story, small yet significant. There are also galaxies so faint they seem almost like illusions. Ultra-diffuse galaxies are spread so thinly across space that their stars barely outshine the darkness behind them. Some are nearly as large as the Milky Way in diameter, yet contain only a tiny fraction of its stars. They appear as pale smudges in deep sky surveys, ghost-like and fragile. Astronomers only began identifying them in significant numbers in recent decades, using sensitive instruments capable of detecting their subtle glow. Their origins remain uncertain. Some may be failed galaxies, systems that lost their gas early, unable to form many stars. Others may have been stretched and diluted by gravitational encounters. Whatever their history, they drift quietly through the universe, enormous yet barely visible. It is possible that many more remain hidden, their light too faint to distinguish from the cosmic background, galaxies shining like fading breath. In crowded galaxy clusters, gravity orchestrates even stranger events. Galaxies tug at one another, exchanging momentum in close passes. Occasionally, these interactions become extreme. A galaxy can be flung outward entirely, ejected from its cluster at tremendous speeds. These runaway galaxies become solitary wanderers, hurled into intergalactic space. Some leave behind long tails of gas and stars, evidence of their dramatic departure. Others carry only their compact cores, isolated islands drifting through vast emptiness. In a universe governed by gravity, even galaxies can be launched into exile. Our own galactic center holds secrets of a brighter past. Today, the core of the Milky Way appears relatively calm. The supermassive black hole, known as Sagittarius A*, emits only modest radiation compared to active galactic nuclei elsewhere. But evidence suggests it was not always so quiet. Enormous gamma-ray structures called the Fermi bubbles extend above and below the galactic plane, likely remnants of past energetic outbursts. Astronomers have also detected echoes of X-ray flares reflecting off nearby gas clouds, faint memories of activity that occurred millions of years ago. There may have been a time when the Milky Way's core shone like a quasar, briefly transforming our gentle spiral into one of the brightest galaxies in its region of space. Long before humans gazed upward, the center may have blazed with extraordinary intensity. The memory of that era lingers in radiation, written across the sky. On the largest scales imaginable, galaxies themselves trace a hidden framework known as the cosmic web. They are not scattered randomly through space. Instead, they gather along vast filaments composed of dark matter, gas, and luminous matter, stretching across hundreds of millions of light years. Between these filaments lie enormous voids, regions nearly empty, where few galaxies reside. The web structure emerged from tiny fluctuations in the early universe, amplified by gravity over billions of years. Galaxies form where filaments intersect, like cities rising at the crossroads of invisible highways. Computer simulations and large surveys have begun to map this immense network, though much of it, especially the dark matter that defines it, remains unseen. The universe is not only vast, it is interconnected. Even within galaxies, the unexpected can occur. While supermassive black holes typically reside at galactic centers, anchoring their hosts, some have been found offset, tens of thousands of light years from the core. These displaced giants may have been kicked during mergers. When two black holes collide and merge, they emit gravitational waves. If those waves are released unevenly, the newly formed black hole can recoil, launched through space like a cosmic cannonball. In other cases, dual black holes may orbit each other, one drifting slightly from center. These wandering black holes still influence surrounding stars and gas. They move quietly through their host galaxies, detectable only through unusual stellar motions or bright emissions. Even the centers of galaxies, it seems, are not always fixed. And when we look far into the distance toward the earliest galaxies, we encounter a final, profound effect: redshift. Light travels at a constant speed, but the space through which it moves is expanding. As the universe stretches, so too does the light within it. Its wavelength lengthens, shifting toward the red end of the spectrum. For the most distant galaxies, this shift is so extreme that light once visible has become infrared by the time it reaches Earth. By measuring this redshift, astronomers determine distance and age. The farther a galaxy lies, the more its light has been stretched, like a note drawn out across cosmic time. In that stretched light is a record of expansion itself, a reminder that the universe is not static, but unfolding. Galaxies drift along filaments. Black holes flicker and fade. Spiral arms flow like currents. Dwarfs orbit patiently. Runaways wander alone. And through it all, ancient light continues its journey, arriving softly at our telescopes, carrying whispers from across billions of years, inviting us to listen and to remember that we are part of this vast, connected, ever-evolving story. Some of the earliest galaxies we have ever glimpsed do not shine in visible light at all. Their ancient starlight, born in a universe still young and turbulent, has been stretched by the steady expansion of space itself. Over billions of years, as the fabric of the cosmos gently unfurled, their light lengthened, reddened, and slipped beyond the reach of human eyes into the infrared. To see them, we must build instruments that can sense warmth rather than color, telescopes that do not merely look, but feel the faint heat of creation. The James Webb Space Telescope was designed for this very purpose, to peer through time by capturing infrared whispers from the edge of the observable universe. And there they are, small, distant galaxies whose light began its journey more than 13 billion years ago. The universe has changed their light, stretched it like a melody drawn out across eternity, but it has not erased it. That ancient glow, altered yet persistent, arrives softly at our detectors. It is proof that even as space expands and epochs pass, the past remains reachable. But galaxies are not static relics suspended in darkness. They are restless. They grow. Some of them are still actively consuming their neighbors. Galaxies do not simply collide and drift apart. Often they devour. A larger galaxy's gravity reaches outward, tugging at a smaller companion, drawing it closer over millions and billions of years. Stars are stripped first, pulled into faint arcs. Gas follows, siphoned away and compressed. Eventually, the smaller galaxy loses its coherence, dissolving into the larger one's halo. This quiet consumption is known as galactic cannibalism. It is not rare. It is not extraordinary. It is one of the fundamental ways galaxies grow. In deep sky images, astronomers see delicate tidal streams, thin trails of stars stretching behind disrupted systems, luminous scars marking recent mergers. Some galaxies host multiple small satellites in the process of falling inward. Others are visibly distorted, their shapes warped by gravity as they absorb a companion. Our own Milky Way is engaged in this slow feast. Nearby dwarf galaxies are being drawn in one by one, their stars gradually woven into our halo. The growth of galaxies is not explosive, it is patient. Over billions of years, they reshape themselves, adding mass not in sudden bursts, but in steady acts of gravitational assimilation. And yet, not all galaxies reveal themselves easily. Some are so rich in dust that visible light cannot escape them. Thick clouds of microscopic carbon and silicate particles absorb starlight, hiding entire structures behind opaque veils. To optical telescopes, these galaxies may appear faint or even invisible, dim shadows against the cosmic background. But dust does not destroy light. It transforms it. Absorbing shorter wavelengths, dust warms and re-emits energy in the infrared and submillimeter range. When observed with specialized instruments, these hidden galaxies glow with surprising intensity. Many of the most vigorous star-forming galaxies in the early universe were discovered this way, brilliant nurseries concealed behind curtains of cosmic soot. Within these dusty systems, stars are born at astonishing rates. Stellar winds and supernovae enrich the environment with heavier elements, creating more dust, continuing the cycle. Their visible light may be obscured, but in thermal wavelengths they shine like embers beneath ash. Without infrared astronomy, we might never have known they existed. Entire chapters of cosmic history would remain unread. In the crowded environments of galaxy clusters, another subtle force shapes galactic evolution. Clusters are not empty voids between galaxies. They are filled with a thin, extremely hot plasma known as the intracluster medium. Though tenuous, this gas can exert pressure on galaxies moving rapidly through it. As a galaxy plunges into a cluster, it experiences a kind of cosmic headwind. This pressure, ram pressure stripping, can sweep gas out of the galaxy, trailing it behind in long, ghostly tails stretching tens of thousands of light years. Once stripped of its gas, a galaxy loses the raw material required to form new stars. Star formation slows, then ceases. Over time, the galaxy fades into a quieter, more passive state. Astronomers have observed these stripped systems in exquisite detail, galaxies with luminous hydrogen tails streaming behind them like ethereal banners. Even in the apparent emptiness of space, resistance exists. Galaxies are shaped not only by collisions, but by the environments through which they travel. Some galaxies shine most brightly not in visible light, but in X-rays. In galaxy clusters, gas can be compressed and heated to millions of degrees. At such temperatures, it emits high-energy radiation detectable only by space-based observatories. The centers of active galaxies, where black holes heat infalling material, can blaze in X-rays. Shock fronts from colliding galaxies and powerful outflows from intense star formation also contribute to this energetic glow. To human eyes, these galaxies might seem serene, but in X-ray vision, they reveal turbulence, pressure, and extreme heat. The universe radiates across a spectrum far broader than our senses can perceive. What appears calm may conceal storms of unimaginable energy. Gravity, too, offers a way to reveal the unseen. Galaxies possess immense mass, not only from stars and gas, but from vast halos of dark matter. We cannot weigh them directly, yet we can measure their influence. When a massive galaxy lies between us and a more distant object, its gravity bends the background light in a phenomenon known as gravitational lensing. The degree of bending depends on mass. By carefully analyzing arcs, rings, and distortions in background galaxies, astronomers calculate the total mass of the foreground lens, including its invisible dark matter. In this way, gravity becomes a scale. Even components that emit no light leave measurable fingerprints in the curvature of space. Some galaxies are so enormous they challenge our sense of proportion. While the Milky Way spans about 100,000 light-years, certain supergiant ellipticals stretch more than 1,000,000 light-years across. Among the largest known is IC 1101, a colossal system at the heart of a galaxy cluster. These giants likely grew through repeated mergers over billions of years, absorbing countless smaller galaxies. Unlike spirals, they are smooth and diffuse, their stars distributed in all directions without prominent arms. Their light gradually fades into an extended halo, blending seamlessly into surrounding space. They stand at cluster centers like ancient monarchs, massive, patient, quietly dominant. Meanwhile, our own galaxy is far from stationary. Relative to the cosmic microwave background, the afterglow of the Big Bang, the Milky Way is moving at nearly 600 kilometers per second. This motion reflects the combined influences of our orbit within the galaxy, the Milky Way's approach toward the Andromeda Galaxy, and the gravitational pull of distant mass concentrations such as the Great Attractor. We feel none of this movement. Everything around us moves together. Yet subtle measurements of background radiation and galaxy velocities reveal our trajectory. We are not on a fixed stage. We are in motion, swept along by gravity, carried through expanding space. Our galaxy is part of a modest cosmic neighborhood known as the local group. This gravitationally bound collection contains more than 50 galaxies spread across roughly 10 million light-years. The dominant members are the Milky Way and Andromeda, followed by the smaller Triangulum Galaxy. Most of the others are dwarfs, faint systems orbiting the larger galaxies or drifting in the outskirts of the group. Over immense spans of time, they tug at one another, merge, exchange stars. Beyond the local group lies an even larger structure, the Laniakea supercluster, an immense network of galaxy clusters and filaments extending hundreds of millions of light-years. Yet within that vast architecture, the local group is our immediate family, a small gathering bound together by gravity's invisible threads. And within this family, the largest member is not the Milky Way. That distinction belongs to the Andromeda Galaxy. Roughly twice as massive as ours, Andromeda contains more stars, a larger central black hole, and a broader stellar halo. Its spiral arms sweep outward in graceful arcs, similar yet grander than our own. Even now, Andromeda approaches us at over 100 kilometers per second. In a few billion years, the two galaxies will merge, blending into a single, more massive elliptical system. It will not be an explosion of chaos, but a prolonged gravitational dance, stars weaving past one another, gas clouds colliding, new stars igniting in luminous bursts. Over time, the merged galaxy will settle into a new equilibrium. And somewhere within it, perhaps carried to a different region of space, our solar system may continue its quiet orbit, witness to yet another transformation in the endless, patient evolution of galaxies. Through infrared light and tidal streams, through dust and X-rays and gravitational arcs, we piece together this vast story. A universe of growth and motion, of quiet cannibalism and luminous rebirth, of expansion stretching ancient light across billions of years. And within it all we drift, small, aware, and profoundly connected to the unfolding of cosmic time. On a clear night, far from city lights, the Andromeda Galaxy appears as little more than a faint blur, an elongated mist suspended in darkness. To the naked eye, it is subtle, almost shy, a pale smudge barely brighter than the surrounding sky. And yet that quiet blur is a vast and intricate system, home to perhaps 1 trillion stars. Within it are countless planets, clusters, nebulae, and a supermassive black hole anchoring its luminous core. Spiral arms sweep outward in grand arcs, woven from gas, dust, and stellar light. Entire civilizations, if they exist, would look out from its worlds and see our Milky Way as their own distant blur. In many ways, Andromeda is our galactic twin, similar in structure, similar in age, similar in the patient way it has grown by merging with smaller companions over billions of years. And one day, long after our present constellations have shifted beyond recognition, Andromeda will not merely be our neighbor. It will become part of our shared future self. But even now, before that distant union, something unseen surrounds both galaxies. Around every large galaxy lies an invisible halo of dark matter. It emits no light. It reflects nothing. It absorbs nothing. And yet its presence is undeniable. It exerts gravity, immense gravity, extending far beyond the visible stars into a vast spherical envelope. Astronomers first sensed these halos not through sight, but through motion. When they measured how stars orbit near the edges of galaxies, they found something unexpected. The outer stars were moving far faster than visible mass alone could account for. By all known laws of gravity, they should have drifted away into space. Yet they remained bound. There had to be more mass than we could see. That hidden mass, dark matter, outweighs ordinary matter in the universe by more than 5 to 1. Galaxies are embedded within these halos, likely formed inside them, shaped by the gravitational scaffolding of something still mysterious. Without dark matter, galaxies would not hold together. Clusters would disperse. The cosmic web would unravel. We cannot see these halos directly, but their influence is written into the rotation of stars, the bending of light, and the clustering of galaxies. The universe, it seems, is held together by something we have yet to touch. Closer to home, if you stand beneath southern skies, you might notice 2 luminous patches detached from the familiar band of the Milky Way. They resemble faint clouds drifting in the night, but they are not clouds at all. They are galaxies. The Large Magellanic Cloud and the Small Magellanic Cloud are irregular dwarf galaxies, orbiting the Milky Way at distances of roughly 160,000 and 200,000 light-years. Cosmically speaking, they are close neighbors. Each contains millions of stars, along with clusters and vast reservoirs of gas. Within the Large Magellanic Cloud lies the breathtaking Tarantula Nebula, one of the most active star-forming regions in our local universe, a luminous cradle where massive stars ignite in brilliant clusters. These 2 dwarf galaxies are not merely passive companions. They interact with each other as they orbit us, their gravitational dance complex and evolving. Evidence suggests they may be relatively recent arrivals, perhaps captured within the last few billion years. As they circle the Milky Way, gravity gently tugs at them, pulling stars and gas outward. Behind them stretches a faint ribbon of hydrogen gas known as the Magellanic Stream, a vast, elongated structure trailing across the sky for hundreds of thousands of light years. Alongside it are stellar streams, individual stars torn loose and drawn into the Milky Way's halo. These trails are like footprints across deep time, subtle, fading, yet revealing the path taken. They allow astronomers to map the shape of our galaxy's gravitational field and to understand how interactions sculpt cosmic structures. Though the Magellanic Clouds remain intact for now, their drifting echoes remind us that no orbit is simple and no companion remains unchanged forever. Beyond individual galaxies, gravity weaves larger tapestries. Galaxy clusters can contain hundreds or even thousands of galaxies bound together in colossal assemblies. When astronomers measured the visible matter within these clusters, the stars, gas, and dust, it became clear that it was not enough to keep them gravitationally intact. The galaxies were moving too quickly. Again, dark matter emerged as the unseen anchor. Most of a cluster's mass resides in invisible halos that envelop the entire system. This hidden mass slows galactic motions and prevents clusters from flying apart. We detect it indirectly, through galaxy velocities, through the bending of background light, through the temperature of the hot intracluster gas glowing in X-rays. Without dark matter, these clusters would disperse into the void. Instead, they have remained bound for billions of years. Vast islands of light held together by gravity we are still striving to understand. Clusters themselves gather into even greater structures, superclusters. Galaxies form groups. Groups assemble into clusters. Clusters stretch into sprawling superclusters, among the largest known structures in the universe. These immense regions span hundreds of millions of light years, containing thousands upon thousands of galaxies connected through filaments of dark matter. Our own cosmic address extends beyond the Milky Way, beyond the local group, into the Laniakea supercluster. In 2014, astronomers mapped the motions of nearby galaxies and redefined our place within this vast structure. Laniakea, a Hawaiian word meaning immeasurable heaven, spans over 500 million light years and contains more than 100,000 galaxies. It is not a simple sphere. It is a flowing network, with galaxies moving along gravitational pathways toward a central region known as the Great Attractor. Even our Milky Way, traveling at nearly 600 kilometers per second relative to the cosmic background, is gently drawn along these immense currents. We are not just residents of a galaxy. We are inhabitants of a supercluster, drifting within an immeasurable heaven. When astronomers map galaxies on the largest scales, they do not see randomness. Instead, they observe a vast, interconnected framework known as the cosmic web. Galaxies align along delicate filaments of dark matter and gas stretching across hundreds of millions of light years. At the intersections of these filaments lie dense nodes, clusters and superclusters glowing like jewels at the crossings of invisible threads. Between these threads lie immense voids, regions nearly empty of matter. Some span tens or even hundreds of millions of light years. A few lonely galaxies may drift within them, but for the most part they are silent expanses. These cosmic voids formed naturally as matter in the early universe clumped together under gravity, leaving behind underdense regions. They are not mere gaps. They are essential components of the universe's architecture. The web is defined as much by its emptiness as by its light. In these vast voids, some galaxies live in near total isolation. Unlike cluster galaxies constantly shaped by interactions, these field galaxies drift alone. Without neighbors to disturb them, they evolve more gently. Their shapes remain undistorted. Their gas reservoirs are less likely to be stripped away. We do not fully understand how some of these cosmic hermits came to reside in such lonely places. Perhaps they formed in low-density regions from the beginning. Perhaps they were ejected long ago from crowded environments. Whatever their origin, they move quietly through immense emptiness unaccompanied. It is humbling to imagine such solitude on a galactic scale, a single island of stars adrift in a sea of near-nothingness. And yet, whether in crowded clusters or silent voids, Whether bound by dark matter halos or trailing luminous streams, galaxies remain connected to the greater pattern. They move along filaments. They respond to unseen gravity. They grow, merge, and drift within a structure far larger than themselves. The universe is not chaotic emptiness. It is an intricate design shaped by gravity over billions of years, a web of light and darkness, matter and mystery. And within that web, our small planet orbits an ordinary star in one spiral arm of one galaxy among trillions. We are carried through space at extraordinary speed, guided by forces invisible yet precise, embedded within layers of structure that extend beyond imagination. From faint blurs like Andromeda to invisible halos of dark matter, from luminous clusters to silent voids, the cosmos reveals a profound truth. Even in the deepest darkness, there is pattern. Even in vast emptiness, there is belonging. We are not separate from this architecture. We are woven into it, threads of stardust in an immeasurable heaven, drifting gently through a universe both immense and quietly beautiful. In a universe where nearly everything is woven into filaments of gravity and light, where galaxies gather like dew along invisible threads, there are still places of solitude. Even here, on the grandest scales imaginable, isolation has not vanished. Some galaxies drift alone, far from clusters and far from the luminous highways of the cosmic web. They are the quiet hermits of deep time, turning slowly in the dark, untroubled by passing neighbors. In their solitude, they remind us that connection is not the only story the universe tells. There is also stillness. There is also quiet becoming. And then above our small and turning world, a machine opened its golden eye. When the Hubble Space Telescope first rose into orbit around Earth, humanity held its breath. No one knew exactly what it would reveal. We had theories, of course, maps of stars, distant spirals, faint smudges catalogued through ground-based telescopes. But space still felt, in many directions, like a vast and empty sea. In the late 1990s, astronomers made a bold and almost poetic decision. They aimed Hubble at a tiny patch of sky that appeared utterly blank. No bright stars, no famous galaxies, nothing that seemed worthy of attention, just darkness. They let the telescope stare there for days, collecting photons one by one, as if listening for a whisper in the void. What returned was not silence. It was an ocean of galaxies, thousands of them, crowded into a region of sky no larger than a grain of sand held at arm's length. This image became known as the Hubble Deep Field, and later, even more profoundly, the Hubble Ultra-Deep Field. Where we had once imagined emptiness, there was abundance. Where we had seen darkness, there was layered time. Each tiny smear of light in that image was a galaxy. Each galaxy contained billions of stars. Around many of those stars, planets likely circled in patient silence. Some of the galaxies were relatively nearby in cosmic terms, bright and well-formed spirals. Others were faint, reddish glows, their light stretched by the expansion of the universe, traveling more than 13 billion years to reach us. In that small square of sky, we were looking not just across space, but across epochs. We were seeing galaxies as they were when the universe was young, clumsy, compact, still assembling themselves from primordial gas. The image was not a snapshot. It was a cross-section of history, a layered archive of becoming, and a realization settled in. If such a tiny fragment of the heavens held thousands of galaxies, then the full sky, every direction, every dark corner, must be filled with hundreds of billions more. The universe was not sparsely populated. It was richly, overwhelmingly alive with structure. The deeper we looked, the more we found. And with every deeper exposure, the cosmos answered our curiosity not with emptiness, but with astonishing depth. These deep fields are more than photographs. They are time machines. They allow us to see light that began its journey long before Earth formed, before oceans gathered, before life stirred. That light crossed an expanding universe, slipping between filaments of dark matter, skirting clusters and voids, until it finally brushed the mirror of a telescope orbiting a small blue planet. And in that contact, we learned that we are surrounded, always, by galaxies. In the early universe, many of those galaxies were far more turbulent than the quiet spirals we see nearby today. At their centers, enormous black holes were feeding with insatiable hunger. When enough gas spirals into a supermassive black hole, it does not fall silently. It forms a blazing accretion disk, heating to extraordinary temperatures, radiating across the electromagnetic spectrum. The result is a quasar, a beacon so luminous it can outshine its entire host galaxy. Today, quasars are rare. Most large galaxies, including our own Milky Way, harbor central black holes that rest in relative calm. But in the distant past, quasars were common. Young galaxies were rich in cold gas, and their central black holes had ample fuel. For millions of years at a time, these black holes blazed like cosmic lighthouses. Some of the brightest quasars we have ever observed shone when the universe was less than 1 billion years old. We see them now as faint, distant points of light. But what we are witnessing is ancient radiance, the fury of matter spiraling into darkness, transformed into brilliance. Their radiation did not simply illuminate space. It shaped it. The intense energy streaming from quasars could heat and expel gas from their host galaxies, slowing or even halting star formation. In this way, black holes, once thought to be mere cosmic endpoints, became architects. Their outbursts sculpted galaxies, influencing how and when stars would form. Eventually, the fuel ran thin, the feeding slowed, the blaze dimmed. What remains are galaxies with quiet cores, their once ferocious centers now subdued. Quasars are the echoes of a younger, brighter universe, their ancient light still arriving at our telescopes, whispering of an era when black holes ruled the sky. And yet, even now, we are discovering that these cosmic giants can be more unpredictable than we imagined. For many years, astronomers believed quasars turned on and off only over immense spans of time. Millions of years of steady brilliance, followed by gradual fading. But in recent decades, we have observed something astonishing, changing-look quasars. Galaxies whose cores shift from bright to dim, or dim to bright, within just a few years. On human timescales, 1 year, the galaxy's center flares with the unmistakable signature of an active black hole. The next, it has faded, as though someone has lowered the cosmic volume. Sometimes the light returns. Sometimes it flickers again. These changes are likely caused by fluctuations in the flow of gas toward the black hole. A sudden surge, a blockage, a collapse in the inner disk. It means that even at the hearts of galaxies, variability is possible. Even the most massive and seemingly eternal engines can have moments of quiet and sudden light. The universe, vast as it is not frozen. It breathes. It shifts. It pulses. And the light from some quasars has traveled more than 10 billion years to reach us. When we look at one, we are peering into a time before Earth existed, before our sun ignited, before the Milky Way had fully assembled its graceful spiral arms. That light has crossed expanding space, stretched into longer, redder wavelengths by the growth of the cosmos itself. It has endured dilution and distance, and yet it still carries the fingerprint of extreme energy, a signature of matter plunging toward a black hole in a galaxy long changed. To observe a quasar is to open a narrow tunnel through time. It is to connect across unimaginable distances with a universe in its youth. Closer to home, galaxies continue their silent choreography. They do not drift aimlessly. They spin. Stars orbit galactic centers, tracing vast circular paths governed by gravity. In some galaxies, these rotations are so rapid that the outermost stars move at extraordinary speeds, hundreds of kilometers per second. Fast enough, it would seem, to escape, and yet they do not. What holds them is not only the gravity of visible stars and gas, but the embrace of dark matter halos, vast, invisible spheres of mass that surround galaxies and extend far beyond their luminous edges. It was the unexpected speed of these outer stars that first hinted at dark matter's existence. Without additional unseen mass, the galaxies should have flown apart. Instead, they remain bound, motion balanced by hidden gravity, a quiet tension between outward momentum and inward pull. The faster the stars move, the stronger the unseen arms that hold them close. Some galaxies take on even stranger forms. There are polar ring galaxies, systems where a main galactic disk spins in one plane, while a second ring of stars and gas orbits at a near right angle, encircling the galaxy's poles. These structures likely form during close encounters or collisions, when material from one galaxy is captured and settles into a new orbit, shaped by gravity into a luminous ring. From afar, they resemble cosmic wheels turning along two axes, layered currents in deep space, moving independently, yet held within a shared gravitational field. They are rare, elegant, and quietly peculiar, reminders that the universe delights in variation. And then there are ring galaxies shaped like luminous halos or enormous celestial donuts. These often arise when a smaller galaxy plunges through the heart of a larger one. The gravitational disturbance sends waves rippling outward, compressing gas into expanding rings where new stars ignite in brilliant arcs. The center may appear nearly empty, while the outer ring glows with fresh blue light. Though born of collision, they achieve a new equilibrium. The aftermath of violence becomes symmetry. Stars orbit in balance, tracing the memory of an encounter that may have occurred a billion years ago. Elliptical galaxies tell a different story. Unlike spirals with their graceful arms, ellipticals are rounded and diffuse, their light smooth and even. Inside them, stars do not share a common direction of spin. Instead, they move in random orbits, some circular, others elongated, each tracing its own path through a gravitational field shaped by past mergers. Many elliptical galaxies are the products of collisions between spirals. When galaxies merge, the orderly rotation of their stars is disrupted. Over time, the system settles into a more spherical form, but the memory of chaos remains in the randomness of stellar motion. These galaxies are often older, containing little cold gas and forming few new stars. Their glow is steady and subdued, like a lingering twilight. Within them, however, every star is in motion, a quiet storm held together by gravity. And not all galaxies fit neatly into spirals or ellipses. Some appear torn, stretched, asymmetrical. Irregular galaxies often bear the scars of gravitational encounters. Pulled and distorted by larger neighbors, their stars scatter into uneven shapes, their gas compressed in some regions and dispersed in others. They resemble luminous clouds adrift in a vast night. Yet even in their irregularity, there is coherence. Gravity still binds them. Stars still shine. New generations may still form from compressed gas. They are reminders that structure in the universe is not always symmetrical. Beauty can emerge from disruption. Stability can arise from chaos. Across all these forms, spirals, ellipticals, rings, polar structures, irregular clouds, the universe tells a consistent story, gravity shaping light across deep time. We are small within this immensity, a species on a planet circling a single star in one galaxy among hundreds of billions. And yet, through patient observation, through instruments like Hubble and the quiet dedication of countless minds, we have traced the outlines of the cosmic web. We have seen galaxies flicker and merge. We have mapped halos we cannot see and watched light that began its journey before Earth was born. In the silent drift of isolated galaxies, in the blazing youth of quasars, in the layered depths of deep field images, we glimpse something profound. The universe is structured, dynamic, and interconnected, and still within that vast connection, there is room for solitude, for quiet rotation, for light traveling billions of years simply to arrive. Some galaxies never quite found a single dominant shape. They did not grow elegant spiral arms, nor settle into the smooth glow of an ellipse. Instead, they formed as scattered constellations of stars and gas, clumps drifting together in loose communion. From afar, they can resemble fragments of something broken, as if pieces of a larger design were scattered across the dark. And yet, they are whole in their own way. These irregular galaxies are often rich in hydrogen, the primordial breath of the cosmos. Within them, young, hot stars burn blue and brilliant, illuminating tangled clouds of gas. They are places of restless activity, where gravity has not yet sculpted symmetry, where turbulence still speaks louder than order. Some may be early in their story, still assembling themselves from smaller pieces. Others may have been shaped by past encounters, their structures stirred and stretched by the passing gravity of larger neighbors. For now, they drift as luminous patchworks, chaotic yet alive. In their uneven glow, we are reminded that evolution does not always move in straight lines. Sometimes it swirls, sometimes it fractures, and sometimes, from apparent disorder, new forms slowly emerge. There are galaxies that burn with sudden intensity, as if time itself has briefly accelerated within them. These are the starburst galaxies. In most galaxies, stars are born gradually, one generation following another across billions of years. But in a starburst galaxy, that rhythm quickens dramatically. Clouds of gas collapse in rapid succession, igniting waves of star formation hundreds, or even thousands of times faster than usual. Such a burst may be triggered by a merger, when two galaxies draw close and their gravitational embrace compresses vast reservoirs of gas. It may follow a near miss, or the shockwave of a previous collision. Whatever the cause, once the compression begins, it is as though a match has been struck in a dry forest. New stars blaze into existence, flooding the galaxy with ultraviolet light. Dust absorbs this brilliance and re-emits it in infrared, so that these galaxies glow intensely across wavelengths. Yet the frenzy cannot last. The fuel is finite. Within just a few million years, a fleeting instant in cosmic time, the gas is consumed or expelled. The firestorm subsides. What remains is a transformed galaxy. A fresh population of young stars shines where once there was only diffuse gas. The dust still glows faintly, a lingering warmth from the blaze. Starbursts are cosmic flashes, beautiful, dramatic, and brief. They remind us that even galaxies can experience moments of passion before returning to quiet endurance. And there are galaxies that grow silent. To form stars, a galaxy must hold on to its gas. Without it, there can be no new suns, no fresh constellations kindled in the dark. Over billions of years, stars gradually consume this reservoir. But sometimes the gas is lost more abruptly. A galaxy falling into a dense cluster may have its gas stripped away by the hot intercluster medium, like wind tearing leaves from a tree. Powerful radiation from an active black hole can heat or expel it. Explosions from massive stars can drive it outward. When the gas is gone, star formation slows, then stops. The brilliant blue stars, young and short-lived, fade first. What remains are older, redder stars, glowing softly with the memory of earlier epochs. Astronomers sometimes call such systems red and dead. Yet this phrase hides a gentler truth. These galaxies are not lifeless. They are elders. Their light is steady and subdued, like embers long after a flame has passed. They drift through space not as creators of new stars, but as archives of the past, luminous fossils holding billions of years of history in their quiet glow. Sometimes the very act of creation can push matter away. When stars form in great numbers, they unleash winds, streams of particles and radiation that ripple outward. Supernova explosions add their force, heating gas to extraordinary temperatures. In certain galaxies, especially those in starburst phases or harboring active black holes, These galactic winds become powerful enough to drive material far beyond the galaxy's visible boundaries. We have observed vast plumes of glowing gas streaming away from galactic centers, stretching into intergalactic space. These winds remove the raw material for future stars, reshaping the destiny of the galaxy. A single episode of intense star formation can determine the fate of millions of stars yet unborn. It is as though the galaxy breathes out, exhaling part of itself into the greater cosmos. A breath that changes everything. At the heart of many galaxies lies a supermassive black hole, small in size compared to the galaxy, yet immense in influence. When such a black hole feeds, drawing in gas and dust, it does more than shine. The energy released can heat surrounding gas or hurl it outward in vast jets and winds. This process, known as active galactic nucleus feedback, plays a profound role in shaping galaxies. If the gas is too hot, it cannot collapse into new stars. If it is expelled entirely, the galaxy is left barren of future fuel. In this way, a single invisible object at the center can regulate the growth of billions of stars. Some of the largest galaxies in the universe ceased forming stars billions of years ago, likely because their central black holes once flared so fiercely that they quenched further creation. The center may appear calm today, but its past activity echoes in hot halos of gas and in stellar populations that have long since aged. Even in silence, the memory of energy lingers. Not all galaxies reveal themselves in visible light. Surrounding many of them are vast clouds of hydrogen, the most abundant element born in the early universe. Hydrogen atoms emit a faint radio signal at a wavelength of 21 centimeters. By tuning into this subtle frequency, astronomers can detect galaxies that are otherwise hidden, too faint, too dusty, too distant for optical telescopes. Through these radio whispers, we map a galaxy's rotation and mass. We trace how hydrogen follows the pull of gravity, revealing the presence of dark matter halos that cannot be seen directly. Entire surveys scan the sky in radio wavelengths, charting hydrogen across cosmic time. In this way, even the faintest galaxies leave echoes. Even in apparent silence, there is something to hear. Some galaxies speak most clearly in radio waves. When observed at these long wavelengths, the universe transforms. Certain galaxies display enormous jets of particles streaming from their centers, powered by supermassive black holes. These jets can extend millions of light years beyond the visible edge of the galaxy, forming vast lobes that glow softly in radio maps. Other radio emissions arise from supernova remnants or from cold hydrogen clouds. The shapes can be strange: double sources, arcs, luminous lobes stretching symmetrically across space. Invisible to the human eye, these structures reveal hidden processes of immense energy and scale. In the radio sky, the cosmos appears filled with quiet power, currents and flows unseen in ordinary light. There are also galaxies that hide behind veils of dust. Thick clouds obscure their starlight in visible wavelengths, making them nearly invisible to traditional telescopes. Yet dust is not an absolute barrier. It absorbs starlight and re-emits it in infrared. Through infrared observatories such as the Spitzer Space Telescope and the Herschel Space Observatory, astronomers have uncovered entire populations of infrared luminous galaxies. Within these dusty systems, stars are forming at remarkable rates. Young, hot stars heat the surrounding dust, causing it to glow brightly in far infrared light. For decades, many of these galaxies were almost completely hidden from view. Only by expanding our vision beyond visible light did we begin to see their brilliance. It is a humbling lesson. The universe does not always reveal itself easily. Sometimes its most vibrant regions are cloaked, glowing softly in wavelengths beyond human sight, waiting for patient instruments to discover them. When we look back toward the early universe, toward galaxies whose light has traveled more than 10 billion years, we find forms that seem unfamiliar. These ancient galaxies are smaller, clumpier, more chaotic. Their stars are younger and more metal-poor, forged from material that had not yet been enriched by many generations of stellar evolution. They are galaxies still assembling themselves, merging, colliding, growing through accretion and star formation. Their shapes have not yet settled into the graceful spirals and smooth ellipses we see nearby. Instead, they appear as luminous knots embedded in a turbulent cosmic landscape. Over billions of years, these early systems merged and matured. They built the grand structures of the present universe. When we observe them now, we are witnessing adolescence on a cosmic scale, imperfect, energetic, full of possibility. And if we look even further back, beyond adolescence, we approach the first light. There was a time after the Big Bang when the universe was dark. No stars burned, no galaxies shone. Space was filled with cooling hydrogen and helium, expanding into silence. This era, sometimes called the Cosmic Dark Ages, lasted for hundreds of millions of years. Then, slowly, gravity gathered matter into the first dense pockets. The first stars ignited. Their light pierced the darkness. The first galaxies assembled around them. This period, the Cosmic Dawn, began roughly 200 to 400 million years after the beginning of time. With instruments like the James Webb Space Telescope, we are now beginning to glimpse that distant era. We see tiny, bright galaxies, astonishingly luminous for their size. They form stars rapidly, bathing their surroundings in radiation that reionized the neutral hydrogen filling space, gradually lifting the cosmic fog. Each image from this epoch is a message from the beginning, a record of the universe learning to shine. These first galaxies were small and chaotic, yet they set in motion the grand architecture we inhabit today. When we gaze upon them, we are not merely observing distant objects. We are witnessing the first attempts at structure and light, the moment when darkness gave way to radiance. And in that ancient glow, carried across billions of years, we find a quiet truth. The universe has always been becoming, always assembling itself from simplicity into complexity, from silence into song. It is a distant story, so distant that the mind almost refuses to hold it. And yet, it is the beginning of everything we know. Every star, every atom in your body, every drifting cloud in the Milky Way traces its ancestry back to that early era when the first galaxies began to gather from darkness. In the newborn universe, matter was not spread perfectly smooth. There were tiny irregularities, minute fluctuations in density, born from quantum ripples in the first fractions of a second after the Big Bang. These slight imbalances, almost unimaginably small, became the seeds of structure. Gravity, patient and persistent, began to amplify them. Where the fluctuations were strongest, dark matter gathered first. It formed vast, invisible halos, clouds of mass that did not shine, did not absorb, did not reflect. They were silent wells of gravity, shaping space itself. Inside these halos, ordinary matter, hydrogen and helium gas, began to fall inward. Protected from the chaotic expansion around them, shielded within these gravitational cradles, the gas cooled. It condensed. It fragmented into the first stars. And from those stars, the first galaxies were born. Without dark matter, it is likely these early systems could not have formed at all. The halos provided the structure, the depth, the stability needed in a turbulent young cosmos. They were the invisible architecture beneath the visible light. Even today, every galaxy we observe, from the smallest dwarf to the grandest spiral, appears to live within such a halo. An unseen skeleton surrounds each luminous form. We cannot see these halos directly, but their influence is unmistakable. They guide the growth of galaxies. They determine how stars move. They anchor vast systems against dispersal. The first galaxies were not merely fortunate accidents of gravity. They were held, gently but firmly, by unseen hands. And without those unseen hands, galaxies would not endure. When astronomers began carefully measuring how galaxies spin, they encountered a quiet paradox. Stars orbit their galactic centers at tremendous speeds. In the outer regions, far from the bright core, they move far faster than expected. If only visible matter were present, stars and gas alone, the galaxies should not remain intact. The outer stars should drift away into the dark, unbound by insufficient gravity. But they do not. Instead, galaxies hold their shape. Their stars remain in orbit. The only explanation was the presence of additional mass that emits no light. Dark matter. It does not glow. It does not sparkle. It cannot be photographed. Yet its gravity binds billions of stars into coherent spirals and ellipses. Without it, galaxies would unravel. Their edges would fray into space. The luminous structures we admire would simply scatter. Galaxies shine because of stars, but they endure because of something deeper, something still not fully understood. Our own Milky Way carries this hidden architecture within it. It is not a single flat disk alone. It has layers, a central bulge, a broad spinning disk, and surrounding them both, a wide and diffuse stellar halo. In that halo dwell some of the oldest stars in our galaxy. Many are more than 10 billion years old. They move in elongated, looping orbits that carry them far above and below the galactic plane. Unlike the orderly circular motion of stars in the disk, halo stars wander in arcs and plunges, tracing ancient paths through space. The halo contains very little gas. Star formation there is rare. Its population is made mostly of relics, dim, metal-poor stars that formed when the universe itself was young and heavy elements were scarce. They are fossils of an earlier epoch, preserving in their chemistry the memory of primordial times. By studying these ancient stars, astronomers peer into the Milky Way's distant past, into a time before its spiral arms fully took shape, when it was still assembling itself from smaller pieces. Because not all of the stars in the Milky Way were born here. Over billions of years, our galaxy has collided with and absorbed many smaller companions. These mergers did not happen in violent flashes alone. They unfolded gradually. As a smaller galaxy approached, tidal forces stretched it apart. Its stars were drawn out into long, delicate streams, ribbons of light wrapping around the Milky Way. Some of these stellar streams still trace great arcs across the sky, faint and subtle. By mapping their positions and measuring their motions, astronomers can reconstruct the story of each ancient merger, where the original galaxy came from, when it was disrupted, how it was pulled apart by gravity's steady hand. Within the Milky Way today are stars with unusual orbits, stars that move against the general rotation of the disk, stars whose chemical compositions differ from their neighbors. These are immigrants from long-vanished galaxies. Their original homes are gone, dissolved into the larger structure. But their light remains. The Milky Way is not a singular, unbroken entity. It is layered memory, a quiet archive of past encounters, a structure built not in isolation, but through the gradual drawing in of its cosmic neighbors. Even now, the process continues. Galaxies are time machines in another profound sense. Light does not arrive instantly. It travels at a finite speed. When we observe a nearby galaxy, we see it as it was millions of years ago. When we observe 1 billion of light years away, we see it as it was billions of years ago, when the universe itself was young. The farther we look, the deeper into history we peer. Every telescope becomes a portal through time. Each faint galaxy in a distant image is not simply far away, it is ancient. Some appear chaotic and newly formed. Others are already structured and mature. By studying galaxies across a range of distances, astronomers have assembled a timeline of cosmic evolution, from the first sparks of light to the richly structured universe we inhabit today. We do not travel backward in time. The light does that for us. Meanwhile, our own galaxy is in motion. The stars of the Milky Way are not fixed against a static backdrop. They orbit the galactic center at extraordinary speeds. Our solar system, for instance, travels at roughly 220 kilometers per second. It takes about 225 million years to complete a single orbit around the galaxy. That means Earth has circled the Milky Way only about 20 times since it formed. One galactic year spans epochs of life. During a single orbit, dinosaurs rose and fell. Continents shifted. Ice ages came and went. Civilizations appeared in the blink of a cosmic eye. From our perspective, the night sky appears steady. But we are being carried along in a vast spiral dance, circling a central mass we cannot directly see. The galaxy turns slowly, majestically, and we turn with it. Yet galaxies do not rotate like solid objects. If they were rigid like spinning records, the outer edges would move more slowly than the inner regions. But observations reveal something surprising. Stars far from the center orbit just as quickly as those nearer in. The rotation curve remains flat. This puzzling behavior was one of the strongest clues pointing to dark matter. Only a vast halo of unseen mass extending far beyond the visible disk could provide the additional gravity needed to sustain such motion. In the 1970s, astronomer Vera Rubin carefully measured the rotation of spiral galaxies. Her results showed clearly that stars at large distances were moving too fast to be explained by visible matter alone. According to known gravitational laws, they should have drifted away. But they did not. The implication was inescapable. Galaxies contain far more mass than we can see. This unseen component became known as dark matter. It remains invisible to our instruments except through its gravitational influence. Yet from the curves of spinning galaxies, its presence is undeniable. Nearly everything we know about dark matter comes from watching motion. Stars orbiting, galaxies rotating, clusters bound together. It is through movement that the invisible reveals itself. And sometimes, it reveals itself in another extraordinary way, through gravitational lensing. When a massive galaxy or cluster lies between us and a more distant object, its gravity bends the light of the background source. Space itself is curved by mass, and light follows that curvature. The result can be arcs, rings, or multiple distorted images of a galaxy that would otherwise be too faint to detect. In these cosmic lenses, we see not only the distant galaxy magnified, but also the imprint of the invisible mass doing the bending. Dark matter leaves its signature in the distortion of light. It is a strange and beautiful thought that we can discover unseen galaxies not by their own glow, but by the way they warp the light behind them. That invisible mass can become visible through geometry. Across all these scales, from the first dark matter halos to the stellar streams in our own sky, the universe tells a coherent story. Structure emerging from fluctuation, stability arising from invisible support, motion revealing hidden mass. We are part of this grand unfolding, carried through space on a spiral arm, orbiting once every 225 million years, descended from atoms forged in ancient galaxies. It is a distant story, and yet it is our story. Let us continue gently, as though we are drifting through a universe made not only of light, but of memory. When two galaxies begin their long, patient merger, something profound stirs in their hidden hearts. At the center of nearly every large galaxy resides a supermassive black hole, a gravitational anchor so dense and so deep that even light cannot escape its embrace. In our own galaxy, the Sagittarius A** waits quietly at the core, wrapped in silence and orbiting stars. It is not a devourer in constant frenzy, but a still and patient presence, shaping the motion of everything around it. When galaxies merge, their central black holes do not collide immediately. Instead, they begin a slow gravitational courtship. As the galaxies pass through one another, their stars largely slip by untouched, separated by vast distances. But gravity rearranges everything. Over millions of years, the two black holes sink toward the center of the newly forming galaxy, drawn inward by a subtle process known as dynamical friction, a gradual loss of momentum as they stir and scatter surrounding stars and gas. They begin to orbit each other. Imagine two invisible whirlpools in the fabric of space, circling closer and closer in a tightening spiral that can last hundreds of millions of years. Around them, stars trace new paths. Gas clouds compress and ignite fresh waves of star birth. The galaxy reshapes itself, tails fading, distortions smoothing, chaos settling into structure. And at the core, the black holes continue their quiet approach. Eventually, when they draw close enough, something extraordinary happens. Their orbit accelerates. Space itself begins to tremble. As predicted by Albert Einstein in his theory of general relativity, accelerating massive objects generate ripples in space-time, gravitational waves. These waves travel outward at the speed of light, stretching and compressing the very geometry of the cosmos as they pass. When two supermassive black holes finally merge, they release an immense surge of gravitational energy. Not as light, not as sound, but as distortions in the invisible structure of reality itself. For a brief moment, the newly formed black hole may recoil slightly, nudged by asymmetries in the waves it emits. Then it settles, larger and deeper than before. Two gravitational wells have become one. This is not a violent explosion in the way we imagine collisions on Earth. There is no shattering impact, no fire in the conventional sense. It is a transformation, slow, inevitable, written into gravity's quiet laws. Over billions of years, galaxies grow this way, merging, absorbing, reshaping. Their central black holes grow with them, each merger adding mass, deepening the darkness at the core. And yet, despite their immense power, these black holes do not dominate every moment. Galaxies continue to form stars. Planets continue to circle suns. Life, where it arises, may never notice the slow gravitational dance unfolding tens of thousands of light years away. It is humbling to realize that our own galaxy has likely undergone such mergers in its past, and will again. In about 4 billion years, the Andromeda Galaxy will approach the Milky Way, drawn together by mutual gravity. Their spiral arms will stretch and distort. Star formation will surge. And at their centers, two supermassive black holes will begin the same ancient spiral toward union. By then, the Sun will be older, Earth profoundly changed. Whatever stories humanity is telling, if any remain, will unfold beneath a sky transformed. The familiar band of the Milky Way will blur and brighten as Andromeda fills the heavens. It will not be a sudden catastrophe. It will be a slow, luminous reshaping across hundreds of millions of years. Galactic time is different from ours. A single merger can span longer than complex life has existed on Earth. Entire species rise and vanish during the first approach of two spirals. Continents drift. Ice ages come and go. Meanwhile, at the scale of galaxies, the dance continues, patient and immense. And beyond individual mergers, there is the larger structure, the cosmic web itself, binding galaxies across hundreds of millions of light years. Along vast filaments of dark matter, galaxies flow like do along invisible threads. Clusters gather at intersections, glowing nodes in a grand three-dimensional tapestry. Between them lie enormous voids, regions so empty that a lone galaxy can drift in near solitude for eons. Nothing in the universe is truly isolated. Every galaxy belongs to this network. Every star within a galaxy orbits within a deeper gravitational architecture shaped by dark matter halos. The same unseen scaffolding that allowed the first galaxies to form in the early universe. And so we return gently to that beginning. Tiny fluctuations in density, born from quantum tremors in the first fractions of a second after the Big Bang, grew under gravity's steady pull. Dark matter gathered first, forming halos, invisible wells into which gas could fall. Inside those wells, the first stars ignited. Their light began the long journey toward us, crossing billions of years. Some of that light is only now arriving. When we observe a distant galaxy whose light has traveled 13 billion years, we are not merely looking far away. We are looking back to a time when the universe was young, when galaxies were still assembling, when black holes were just beginning to grow. The telescope becomes a bridge across epochs. The night sky becomes an archive. We exist in the middle of this unfolding story, not at the beginning, not at the end. Our planet circles an ordinary star in the outer arm of a spiral galaxy, embedded in a dark matter halo, connected by filaments to clusters and superclusters stretching beyond comprehension. Our entire galactic year, 225 million Earth years for one orbit, is but a small measure within a universe nearly 14 billion years old. The stars we see above us seem still, but they are moving. The galaxy is rotating. The cosmic web is evolving. Distant galaxies are receding as space expands, their light reddening into infrared whispers. Some have already crossed the cosmic horizon, their future light destined never to reach us again. And yet, here we are aware. Small certainly, fragile undeniably, but also capable of tracing these patterns, of discovering dark matter through the rotation curves measured by astronomers like Vera Rubin, of detecting gravitational waves from merging black holes, of mapping stellar streams left behind by ancient galactic meals. We are made of atoms forged in long-dead stars, stars that may themselves have formed in galaxies long since merged into the Milky Way. In a quiet sense, we carry within us the memory of those mergers. The iron in our blood, the calcium in our bones, the oxygen in every breath, all assembled in stellar furnaces scattered across cosmic time. The universe is not static. It is a story of gathering and drifting, of spirals tightening and halos holding, of light bending around mass and mass shaping light. It is a choreography written in gravity and illuminated by stars. And as galaxies continue their slow dances, merging, lensing, rotating, stretching with the expansion of space, we float along within one of them, carried on a spiral arm, orbiting a modest star, wondering. The night sky above us is not just decoration. It is motion. It is history. It is deep time made visible. And in its vast, quiet turning, we are both fleeting and connected. A brief flicker of awareness in a cosmos that has been unfolding for billions of years, and will continue long after our own galactic orbit completes its next slow arc through the dark. We are small, but we are part of the dance. These ghost galaxies are like whispers in the cosmos. Alone, they drift through the near vacuum of intergalactic space, far from the bustling neighborhoods of clusters and filaments. Their stars are sparse, their gas thin, and their light faint, but they are not inert. Gravity still guides them, shaping their slow orbits, bending their paths around invisible dark matter, carrying them through billions of years of cosmic time. Some may have once belonged to a cluster, ejected by interactions with more massive galaxies, flung into solitude by the pull and push of gravitational tides. Others may have quietly formed in isolation, small seeds of stars in regions where gas was too diffuse for large structures to emerge. Each ghost galaxy is a survivor, a relic of a quieter, less crowded part of the universe. Despite their faintness, they are not irrelevant. Even these solitary galaxies participate in the cosmic ballet. Their motions trace the gravitational landscape, revealing the unseen distribution of dark matter. Their stars preserve ancient chemical histories, fossils of star formation in regions far from the dense hubs of galaxies. Their existence challenges our ideas of where galaxies should be, reminding us that the universe is vast, varied, and often surprising. Ghost galaxies drift for billions of years, sometimes slowly approaching clusters or other structures, sometimes continuing in isolation almost indefinitely. Their light is faint, but persistent, and carries the story of formation, survival, and adaptation in the sparsest reaches of space. They are quiet witnesses to the grand narrative of the cosmos, proving that even in the most empty stretches of the universe, motion, history, and structure persist. In the end, galaxies, whether part of bustling clusters, tangled in mergers, or drifting alone as ghostly travelers, all share the same fundamental nature. They are collections of stars, gas, dust, and dark matter bound together by gravity. They grow, interact, collide, and fade. They are time capsules, stretching across billions of years. And in observing them, we see not only the story of the universe, but echoes of ourselves. Small observers trying to understand the vast, dynamic, and interconnected cosmos in which we live. Would you like me to continue into how these ghost galaxies might eventually be captured or fade entirely over cosmic time? Galaxies drift quietly, even in the most remote corners of the universe. We don't always see them by their own light. Some are almost invisible, their stars so sparsely scattered that the galaxy seems like a faint mist, barely there against the dark. These ultra-diffuse galaxies carry as many stars as a dwarf galaxy, yet they stretch across regions as large as the Milky Way. From a distance, they are ghosts, subtle clouds lingering in the void. They may have formed this way, or perhaps tidal forces pulled them apart over time. Some hold almost no dark matter, others seem dominated by it. Their existence challenges what we think we know about how galaxies hold together. Fragile, faint, overlooked, yet persistent, they whisper a story simply by surviving. Galaxies can leave long trails of lost gas behind them. In dense environments like galaxy clusters, a moving galaxy can have its gas stripped away by the pressure of hot plasma filling the space between galaxies. These streams, ram pressure tails, stretch behind like the wake of a ship, glowing in ultraviolet or radio light. Sometimes stars are born along these trails, far from the galaxy's core. Sometimes the gas simply drifts, cooling and fading. These silent traces tell of motion, of loss, of change, stretching across space like memory itself. At the other extreme, some galaxies are ultra-compact, tiny, dense, packed with stars, only a few hundred light-years across, yet containing millions or billions of stars. Some are the remnant cores of once larger galaxies stripped down by gravity. Others formed dense from the start. A star in one of these galaxies may have thousands of neighbors within a single light year. Their light is bright, their structure tight, yet their small size makes them easy to overlook. They are cosmic pressure points, stars compressed into the smallest possible space, glowing quietly but intensely. Some galaxies appear almost like fog, so diffuse, so tenuous, that they barely resemble galaxies at all. Often found in clusters, they may contain almost no gas. Some may be remnants of larger systems torn apart by gravitational forces. Others may have been ghostly from birth, never dense enough to shine brightly. Careful imaging and long exposures reveal their soft glow, but even then they seem ephemeral. These galaxies defy what we expect. No defined structure, no luminous spiral, no bustling star formation. Yet they are bound by gravity, moving, evolving, persisting. Like mist clinging to the edges of space, they float quietly, almost forgotten, yet still part of the universe's story. The universe is expanding, and over unimaginable time, galaxies will drift beyond our reach. Space stretches, carrying them away. One day, far in the future, an observer might see only the galaxies bound to their own, Andromeda, the Milky Way, and a few companions. Everything else will recede past the cosmic horizon. It is not the galaxies themselves fleeing, but space itself expanding, carrying them silently into isolation. What we see now, the rich, structured, glowing cosmos, is a fleeting moment. A window slowly closing. Galaxies are more than light in shape. They are archives of time. From the first gas clouds after the Big Bang to the vast systems we see today, galaxies are the backbone of cosmic history. They reveal how matter organizes, how stars are born and die, how black holes feed and fade. Early galaxies burned fast, chaotic and brilliant. Later galaxies grew stable, structured, luminous in quiet persistence. Every collision, every burst, every slowing into calm leaves a mark. Galaxies evolve, and in their evolution, we see the universe itself maturing. Look closely, and each galaxy is a record of what has been. Stars preserve ancient chemistry. Orbits trace mergers long past. Shapes reflect billions of years of growth and stillness. They are evidence that change is constant, that memory persists across light years, and that even fading light can leave an echo. In the end, a galaxy is both distant and familiar. It holds the past, shapes the present, and hints at futures beyond our imagination. Thank you for traveling here, for listening, for drifting through spirals, halos, arcs, and whispers of stars. Some shone brightly, others barely murmured. Each held a story, written in starlight. And now the sky is quiet again. The facts may fade, but the feeling remains. The vastness, the motion, the humility of being small beneath something eternal. Let the faults drift away. Let the rhythm of galaxies become your own. No more questions tonight. No more discoveries. Just space. Just calm. Just sleep. Good night, and may the stars watch over your dreams.